This is MSJ Chem. In this video, I'll be looking at calculating the pH of weak acids and bases. In our first example, we'll calculate the pH of a weak acid. A 0.5 mole per decimeter cube solution of ethanoic acid has a Ka of 1.8 times 10 to the negative 5. Calculate the pH of the solution. Here we have the equation for the reaction of ethanoic acid and water. The products are the hydronium ion and the ethanoate ion. And here we have the expression for the Ka, the acid dissociation constant. The first step is to draw up an icebox. I stands for initial concentration, change in concentration, and equilibrium concentration. The initial concentration of the ethanoic acid is 0.5 moles per decimeter cubed. The initial concentrations of the hydronium ions and the ethanoate ions are 0. The change in concentration is minus X for the ethanoic acid and plus X for the hydronium ions and the ethanoate ions. So this gives us an equilibrium concentration for the ethanoic acid of 0.5 minus X, and X for the hydronium ions and the ethanoate ions. Because ethanoic acid is a weak acid, we can make the assumption that the equilibrium concentration is equal to the initial concentration. The next step is to input the values into the expression for the Ka. The Ka of ethanoic acid is 1.8 times 10 to the negative 5. X squared is the concentration of the hydronium ions multiplied by the concentration of the ethanoate ions, and 0.5 is the equilibrium concentration of the ethanoic acid. So X is equal to the square root of 9.0 times 10 to the negative 6. And this gives us a value of X of 3.0 times 10 to the negative 3. In the previous slide, we calculated the value of X, which gives us the concentration of hydrogen ions in solution. Next, we'll use this equation to calculate the pH of the solution. So the pH is equal to the negative log of the hydrogen ion concentration, which gives us a pH value of 2.5. In our next example, we'll calculate the pH of a weak base. A 0.2 mole per decimeter cube solution of ammonia has a Kb of 1.8 times 10 to the negative 5. Calculate the pH of the solution. So here we can see the reaction between ammonia and water to produce the ammonium ion and the hydroxide ion. And here we have the expression for the base dissociation constant, the Kb. So here we have our icebox for the reaction. The initial concentration of the ammonia is 0.2 moles per decimeter cubed. The initial concentrations of the ammonium ions and the hydroxide ions are 0. The change in concentration of the ammonia is negative X, and for the ammonium ions and the hydroxide ions it's plus X. This gives us an equilibrium concentration of ammonia of 0.2 minus X. And for the ammonium ions and the hydroxide ions we have X. However, because ammonia is a weak base, we'll make the assumption that the equilibrium concentration is equal to the initial concentration. The next step is to input the values into the expression for the Kb. So the Kb of ammonia is 1.8 times 10 to the negative 5. X squared is the concentration of the ammonium ions multiplied by the concentration of the hydroxide ions. And 0.2 is the equilibrium concentration of the ammonia. So X is equal to the square root of 3.6 times 10 to the negative 6. This gives us a value of X of 1.9 times 10 to the negative 3. In the previous slide, we calculated the value of X, which is the concentration of hydroxide ions in solution. Next, we'll calculate the pOH value. The pOH is equal to the negative log of the hydroxide ion concentration, which gives us a pOH value of 2.7. At 298 K, the pH plus the pOH is equal to 14. Therefore, the pH is equal to 14 minus 2.7, which gives us 11.3.